Okay, welcome to this discussion about Mendelian inheritance. And on page 1 of your notes, you can see a photo of someone, a portrait photo. What is distinctive about this photo is the appearance of dimples, okay, on the cheeks of this person. So what is clear is these are genetic traits, okay? So it's something that is coded for by some genes which you carry in DNA. And these genetic traits, like dimples, they are inherited in a simple pattern, okay? They are inherited in a simple pattern. So because their inheritance is through a simple inheritance pattern, then what we now have to think about is offsprings will have dimples likely if their parents had them, because they have to inherit them somehow. They cannot just occur. Okay. So what we now begin to look at is, let's now look at what exactly, why, for example, we say the inheritance of these dimples is simple inheritance. So what is this simple inheritance? So when you have a trait, for the case of these dimples, if these dimples or any other trait, if it is controlled by one gene, a single gene, and if that gene has two alleles, so the alternative forms, okay, and if one of those two alleles could be completely dominant, so which means once it appears, then it masks the other. Hiyo kama huwa tunaandika R kubwa na R ndogo. So R kubwa will mask R ndogo. Okay? So the inheritance pattern, the way in which inheritance of such a trait will happen if the trait is controlled by a single gene, and that single gene has two alleles, then that mode of inheritance is what we can refer to as a simple inheritance pattern. Okay? But what is more important now is how that inheritance of these simple patterns, simple traits, how it is happening, how it is done, relies on whether the traits are controlled by genes which are located either on autosomes or if those genes are located on sex chromosomes. So autosomes, if you remember, those are chromosomes that don't determine sex. Then our sex chromosomes, those are the ones that determine the sex of an organism. So in human beings, the sex chromosomes is like the X and the Y. Okay? So as human beings, we have 23 pairs of chromosomes. Only one of those 23 pairs is a sex chromosome. Then the other 22 pairs are autosomes. Okay? So it means autosomal traits, so traits which are controlled by genes that are located on autosomes, those are the autosomal traits. So autosomal traits are controlled by genes on one of the 22 pairs of the human chromosomes. So autosomes are all the other chromosomes except X and Y. Okay? So X and Y ndio zinaleta tofauti. So inamaanisha the autosomes do not differ between males and females. Okay? So the autosomes will not be different. But what is different is the sex chromosome. When you have an X chromosome, when you have a Y chromosome. The X chromosome and the Y chromosome, hizo ndio ziko na tofauti. So then that means that traits which are located on autosomes will be inherited in the same way, irrespective if they are coming from the father or the mother. Because remember, the autosomes are just this. Okay? So the only difference in the pattern of inheritance then will be on the sex chromosomes. Okay? But the autosomes the traits on the autosomes will be inherited in the same way. Okay? So that's important to remember. So traits that are controlled by genes that are located on the sex chromosomes are called sex-linked traits. Okay? They are called sex-linked traits. And now when you look at these two sex chromosomes, the X chromosome and the Y chromosome, the Y chromosome is smaller in size. And because of being small in size, it will have fewer genes. Okay, so that then means that the X chromosome has many genes compared to the Y chromosome. So then it means most of the traits that will be sex-linked will be controlled by the many genes on the X chromosome. And now these genes that are on the X chromosome, they are controlling traits, and those traits are now linked to the X chromosome. So we call them X-linked traits. Okay? X-linked traits. So if you are talking of a single gene, okay, a single gene on the X chromosome controlling a trait, okay? So that single gene on the X chromosome controlling a pattern, a certain trait, it will be inherited differently when you compare it with a single gene located on an autosome. Okay? So why is it that the inheritance of a single gene on an X chromosome will be different from the inheritance of a single gene on the autosome? It's because males, wanaume, wako na just one X chromosome. Just one X chromosome. But we have two autosomes. But one X chromosome, one Y chromosome. Okay? So it means that the X chromosome that we have as men, we obtain them from our mothers. Our mothers don't have the Y chromosome to contribute, but our fathers did. So the Y chromosome you have as a male, uliipata kwa baba. The X chromosome you have as a male, you got it from your mother. And the X chromosome you have as a male, you will give it to your daughter. Okay? So the Y chromosome uliipata kwa baba, utapatia your son. The X chromosome, you got it from your mother, you will give it to your daughter. But, so the women, it means the X chromosomes, one of the X chromosomes that they have, waliipata kutoka kwa baba. Then the other X chromosome, waliipata kutoka kwa mama. But for us, our Y chromosome as men, ilitoka kwa baba. Then our X chromosome, ilitoka kwa mama. So that is important because the traits that are now linked on the X chromosome in males, if those traits are to be expressed, then we know imetoka kwa mama. Then the traits that are to be expressed, any traits that is on the Y chromosome, yenye inakuwa expressed in males, hiyo imetoka kwa baba. Okay, so it's important to have that understanding. So that now leads me to the next bit, where now we want to look at how we inherit traits from our parents. Okay, through which patterns. Okay, so how do we study the patterns through which we inherit traits from our parents. So, in order to study that inheritance pattern, there are two critical tools that are used. Because remember, when you are inheriting, it means you are just taking it from one generation to another. We are a different generation, our parents are a different generation, and our children are a different generation. So what we inherited from our parents, there is a way, there are tools that can be used to study that. What we give to our children, there are tools that can be used to study that. Two tools that are critical in doing this, one is the pedigree, and the other one is the Punnett square. So let's begin with the pedigree. So a pedigree is a chart, okay, and it shows how a trait is passed from one generation to another within a family. Okay, within a family. So how far you want to go back into the family is your own thinking. But now, for there to be a family, at least there are father and mother and children. So if you want to go deeper, uende mpaka kwa babu ama uende kwa great grandparent, that's now your decision. But a pedigree is just showing us how traits are passed from one generation to another within a family. Okay. So through a pedigree, we can establish whether a trait is autosomal dominant, autosomal recessive, or if it is linked or located on the X chromosome. Thus we are calling it an X-linked trait. Okay, X-linked trait. So these pedigrees, they will show relationships and help us to identify within these relationships, within this family, which individuals have a given trait. So if you are thinking of sickness, within that family, nani ako na hiyo ugonjwa kwa mfano. Okay. So we'll see on the next page an example of a pedigree. But in that pedigree, we will see that there will be individuals who are affected, who have a certain trait. If the trait in question is a disease, then maybe the affected individuals will be suffering from that disease. Then the individuals who are unaffected, they don't have that disease. So the ones who are affected will be in color red. Okay? The ones who are affected are colored red. The ones who are not affected are colored blue. So we are talking about now either having the trait or not, but not about the gender. So the color is showing us who has the trait, who doesn't have the trait. But now when we go to the second point, it now brings in gender. For there to be family, there must be males, there must be females involved. Because we are talking of sexual reproduction. So there must be a male and a female. Okay. So males in this pedigree will be represented with the squares. Then females, they will be represented in circles. Okay? So wale watakuwa in square ni wanaume. Wale watakuwa circle, those are ladies. Then now in a family, lazima kuna wale wazazi wenye wanaanzisha. So if you are talking of your family, then it is your father and your mother. If you are talking of your extended family, then it is your grandfather and your grandmother. So the top row of any pedigree refers to the first couple. So if it is your family, then it is your father and your mother. That is what the top row will be representing. Then now, because this original couple, being a couple, it means there is a male, there is a female. So they will be breeding. And they are now connected by a horizontal line. So from one member of the couple to another member of that couple, kuna line itatoka kwa huyu iende kwa huyu horizontally. Then now if these two have children, the children will be connected to this couple by a vertical line. So line inatoka kwa hawa couple iteremke chini. Then hawa watoto kama ni wawili, they will be shown hapo chini. We will look at it in the next page. Okay. So all the children that this couple got will be represented in the next row. Okay. So you have the first row of the couple, then the second row of the children. Then if these children also have their own children, which means now the grandchildren of the first couple, the original couple, they will be now on the next row, which is now the third row. Okay? So you can increase pedigrees to as many rows as you want just by showing the additional generations. Okay? You can have as many rows as you want. So the pedigree here is represented as figure 1. And this pedigree here in figure 1 on page 3 is showing an autosomal dominant trait. So those are there are two important words that I want to explain: autosomal and dominant. Autosomal meaning the gene that codes for this trait that we are looking at in this pedigree is located on an autosome. That's why we are calling it autosomal. Then dominant, kumaanisha there will be one allele that is dominating the other. So there is a dominant allele, there is a recessive allele. Okay, so let's proceed. So in this pedigree, we have the first two. We have a square and a circle. Then the square and the circle are joined together by a line which is running horizontally. So we said a square is male, a circle is female. Then red indicates affected, blue indicates not affected. So it means the first couple for this pedigree was between a male who is affected and a female who is not affected. Then now these two, this original couple, they had children. That's why now they are joined with a vertical line. Then these children come in now in the second row. Lakini in the second row you realize the vertical line yenye inatoka kwa the first couple ikiteremka chini inaonyesha tu kwamba kuna the first child who is an affected male. Then the second child who is a male who is not affected. Why? It is a square and a blue color. The first one is a male who is affected. Why? Is a square with red color. So this is the first child, the second child, the third child. The third child here is a daughter or a female who is affected. Then the fourth is a female who is not affected. Then the fifth is a female who is affected. So as you would expect, these children, they end up also marrying so that they can give birth. So the father and mother gave birth to 1, 2, 3, 4, 5. 5 children. Then out of these 5 children, the first one, who is a male, who is affected, married. Okay, so there is a line that is joining this male to this circle. So he married and gave birth to these 2 kids. A female who is affected and a male who is not affected. The second child, who is a male who is not affected, got married to a female who is not affected. Together, they gave birth to 3 children. The first one is a female who is not affected. Second one is a male who is not affected. The third one is a female who is not affected. The third child of this original couple is a female who is affected, because it's a circle in color red. Being a female who is not affected, another thing we know from this pedigree now is this female has not been partnered. So hajaoleka, hajazaa, okay, hajazaa. The fourth child, who is a female and not affected, pia hajazaa. But now the fifth child, who is a female and is affected, got a partner who is a male and not affected. Then now together they gave birth to these 4. Together these 2 gave birth. So there is a line joining this, and there is a vertical line moving from this joining to the offsprings that these 2 have given birth. So the offsprings for these 2, a male who is not affected and a female who is affected, they brought forth 4 children. The first one is a male who is affected, just like the grandfather. The second one is a male who is not affected. The third one is a female who is affected. The fourth one is a female who is not affected, just like the grandmother. So that is a pedigree. That is a pedigree. You can use this key to study how that trait has been inherited, the pattern of inheritance of from what the father had here. How many kids inherited in the second row? 1, 2, 3. What were their gender? The first affected was a male. The second affected was a female. The third affected was a female. What about the grandchildren to this couple in the third row? The first affected was female. The next to be affected was male. The third to be affected was female. Okay? So this is a pedigree that is showing us how an autosomal dominant trait, the pattern through which it has been inherited. The pattern through which it has been inherited. Okay? So it is an autosomal dominant trait. And in this case then, a child has the trait, will always have at least one parent with that trait. Because for you to have a trait being expressed in a child, then the parent must have had it at some point. Okay? But if you are talking of an autosomal recessive trait, then it is possible that 2 individuals who don't have that trait can have a child with the trait. How is that possible? It just means the 2 individuals were heterozygous. When they are heterozygous, they have a dominant allele and a recessive allele. So the dominant one will mask the recessive one. But if those 2 individuals give birth together, if they have a child together, then that child, there is a quarter probability that that child might inherit the recessives that both of them carry. So in an autosomal dominant trait, if you see a child expressing a trait, then it means at least one of the parents had that trait. At least one of the parents had that trait. Okay? So when we go back, for example, when you look at the third row, when you go back to our pedigree, when you look at the third row, which are now grandchildren, anytime there is an affected child, you go up and you realize the parent, one of the parents must have been affected. Okay, one of the parents must have been affected. So you look at the second case, where there are 3 kids who are not affected by that trait. You go back to their parents, you realize both of them are not affected. But anytime you have a trait that is present and is an autosomal dominant trait, then it means automatically one of the parents must have had it before the child expresses it. Okay? But now, this is figure 2 on page 4. That is figure 2. In figure 2, we are showing a pedigree of an autosomal recessive trait. So the difference between figure 2 and figure 1, while both of them are pedigrees, you realize that in figure 2, the individuals are half-shaded. That will mean they are heterozygous. So if they are heterozygous, then they will not show that trait because the dominant trait will overpower the recessive one. So the phenotype of the dominant trait will be expressed, and the phenotype of the recessive trait will not be expressed. Okay, will not be expressed. So in this example, in this pedigree, 2 heterozygous individuals have 4 children. So this is a heterozygous male. This is a heterozygous female. They are joined, they are a breeding pair, so there is a horizontal line joining them. Then together, they had 4 children. The first one is a normal child, who is female. The second one is a normal child, who is male. The third one is a heterozygous female. Then the fourth one is a homozygous male. Okay, the fourth one is a homozygous male. Those that have 2 colors, those are heterozygous. The ones that have 2 colors are heterozygous. The squares are males, the circles are females. So the first child, who is a normal female, was paired in breeding terms with a heterozygous male. Then together they had 3 children. Out of these 3, 2 are normal, and both of them are, one is a lady, another one is a man. But then there is another man of the 3, a male child, who is heterozygous. The second child, who is a normal male, was paired with a normal female. Together, they produced 2 children, a male and a female, both of them normal. The third child is a heterozygous female, but remained unpartnered. So either hajaoleka ama bado hajazaa. So that's why they don't have a generation coming after them. Then now the fourth is a homozygous male. The fourth is a homozygous male. Okay? This homozygous male was partnered with a normal female. Normal female. Together, they had 4 children. 2 who are heterozygous, one is a male, the other is a female. Then 2 who are normal, one is a female, the last one is a male. Okay, so that's how we interpret that pedigree. So the youngest child is an affected male. Ndio huyu hapa. That's the youngest child of this couple. This is the youngest child. That is the unaffected male. This individual mates with an unaffected female to produce 2 heterozygous children and 2 unaffected children. The original couple's next youngest is a heterozygous female. So when you go this way, this affected male was paired with a female who is not affected, and together they produced 2 heterozygous children, 1 male, 1 female, and 2 normal children, 1 female, 1 male. Okay. So the original couple's second child is an unaffected male who partners with an unaffected female to produce 2 unaffected children. So it's this one. Unaffected male, unaffected female, producing 2 children, both of them who are not affected. Why is it possible that you have heterozygous parents producing children who are producing a child who is normal? In this case, this child is not heterozygous, he's homozygous. So with a parent who is heterozygous, he has a blue and a red, a blue and a red. So it's possible that now this child inherited the father's blue and the mother's blue. Then he became blue all through. Okay? So when you read through, that's how now you interpret a pedigree. Okay? So the original couple's oldest child is an unaffected female whose partner is a heterozygous male. Their children are one unaffected female, then there is another unaffected male and a heterozygous male. Ndio hawa. The first and the second is female, this is male. Both of them are not affected. The third one is a heterozygous male. Is a heterozygous male, and that is now how that interpretation happened. So that is a pedigree. But let's now move to the Punnett square. Let's move to the Punnett square. So a Punnett square, I'm sure you must have been taken through in your high school. So it is a chart as well, which allows you to determine the expected ratios of the possible genotypes when 2 parents give offsprings. So when 2 parents produce offsprings, when you use a Punnett square, you can determine the possible ratio of the genotypes of those offsprings. So anytime you have 2 parents mating, we refer to that as a cross. So those 2 parents is a cross between the 2 parents. Okay. So let's use an example in figure 3. Okay. And in this case is an autosomal gene, meaning the gene is located on chromosomes that don't determine sex. And what is important is that both parents are heterozygous for those particular genes. So it's a diploid organism, and at this particular gene, the mating parents are heterozygotes. Okay? So if they are heterozygotes, it means, if they are heterozygotes, then it means that half of the gametes that are produced by each parent will have a capital A allele, and the other half will have the recessive A, so the small a. The capital A is the dominant allele. Then the small a is the recessive allele. Okay? So if we feel Because this is the male, possibly, and this is the female who are mating. So we'll take these alleles, put them on one side of the Punnett square. Then take these alleles and put them on the other side of the Punnett square. Then because it's a cross, it's like we are multiplying. So where the dominant allele meet, they create a homozygous dominant. Where the dominant and the recessive meet, they create a heterozygous. Equally, where the dominant for this parent meet with the recessive for this parent, they'll give us a heterozygous. But when the recessive of this parent crosses with the recessive of this other parent, they give us a homozygous recessive. The other homozygous we have here was a cross between the dominant allele from one parent and the dominant allele from the other parent. So we have a homozygous dominant. So in this case, if you talk of phenotypes, remember it is a dominant trait. So which means the homozygous dominant and the homozygous dominant and the heterozygotes, all of them will have the same phenotype. Okay? Because the phenotype is on the basis of the presence of the dominant allele. So the dominant allele will mask, itafunika the recessive allele. So recessive allele haitaonekana in terms of phenotype. So in terms of phenotype, we will have 3 yellows and 1 green. That's phenotypic ratio. But in terms of genotype, phenotype is the appearance, but genotype is the genes, the alleles that are present, the genetic constitution of an organism. So in terms now of the genotypes, the ratios, we will have 1 homozygous dominant, 2 heterozygotes, and 1 homozygous recessive. So it's a ratio of 1 to 2 to 1. That is the genotype ratio. But the phenotype ratio was 3 to 1. Okay. So when you talk of predicting genotypes and phenotypes with a Punnett square, I've explained that in figure 3. But here, they want us to use this figure 4 to do an explanation. Okay? They want us to use this figure 4 to do an explanation. So if we look at this figure 4 here on page 6, you have 2 plants that are mating. These are flowering plants. So the one that has an arrow, this is male, this other one is female. So both of them, they are heterozygotes at this, for the trait at this particular gene. So you have a dominant and a recessive, a dominant and a recessive. So when we begin to cross them, when they begin to fertilize, the fertilization is random. Okay? So it is possible that the male will have his dominant allele crossing with the female's dominant allele. If that happens, then we have a homozygous dominant. That will give us this color. Okay? But if it happens that the recessive allele from the male plant will cross or with the dominant allele from the female plant, then we have a heterozygote state, but still the color is the same as the homozygous dominant. Then if it still happens that the dominant allele from the male will meet with the recessive allele from the female, we end up with a heterozygote, same color with the homozygous dominant. But now, if the two recessive alleles, one from the female, the other one from the male, if they meet, then now we have a homozygous case, but it's a recessive now. So the color that is recessive, in this case white, can only be expressed when we have a homozygous recessive situation. A homozygous recessive situation. So in terms of phenotype, we have 3 of the same color, then we have 1 of a different color. So you can have a 3, I don't know if this color is, I don't know this, the name of that color, purple. We can have 3 purple and 1 white. Those are the phenotype ratios. 3 purple, 1 white. But in terms of genotype ratios, you have 1 homozygous dominant, 2 heterozygotes, and 1 homozygous recessive. So 1 to 2 to 1. Okay? So phenotype is about their appearance. In this case, for the flowers, it's about their color. When you are looking at a color, which is as a result of the homozygous dominant alleles, you cannot differentiate that color from the same color that has been created by a heterozygous. But when 2 recessive alleles fuse, when they meet, they now express the recessive phenotype, in this case, white. So in terms of phenotype, you cannot differentiate between a dominant and a heterozygote. But now when you go to the genotypes, that is where now you differentiate. Because you will have homozygous, dominant, you will have heterozygotes, and you will have homozygous recessive. Okay? I hope that is properly understood. So, this is a monohybrid cross, because we are just dealing, we are having just the trait that we are looking at is one. In this case, the color of the flower. That is the trait. That is the characteristic. So if the trait that we are looking for is just one, it means we are only interested with one gene. So it is a monohybrid cross. But there comes a times when now you have to think of a dihybrid cross. Okay. A dihybrid cross. So think of it. For a monohybrid cross, we are only looking at a single gene. But now for a dihybrid cross, then we are looking at more than one gene, 2 genes. So you are looking at 2 phenotypes. Okay? You are looking at 2 phenotypes. So what happened in a monohybrid cross? The Punnett square was in 4 squares. Let's have a look at the Punnett square of the monohybrid cross. Because the gene we are looking at, this is a diploid organism. That gene has 2 alleles. So we only needed to have 1 square for each allele. That's why we have 4 squares for a monohybrid cross. But when you are dealing with a dihybrid cross, then you are dealing with 2 phenotypes, and those 2 phenotypes are most likely as well controlled by 2 different genes. So with the dihybrid cross, then we'll add more squares. Okay? We will add more squares. So we'll add 2 more here and 2 more down. So we end up with 16 squares for the dihybrid cross. So the Punnett square of a dihybrid cross will be divided into 16 squares. Okay? So let's have a look. Let's have a look at an example of two traits in a pea plant. Two traits in a pea plant. So let's think of the color and also the shape. So what is the color? Is it yellow? Is it green? What is the shape? Is it round or is it wrinkled? So is it smooth or is not smooth? Basically, that is what we are looking at. So we'll have that properly outlined in figure 5, okay, where we'll have two generations of crosses. There is a parental generation, then there are two, where two homozygous plants are being crossed. So homozygous. Okay. So a plant that produces yellow and round, which means in this case that plant is homozygous, kumaanisha yellow inakuwa na dominant, so it is the trait for the yellow pea is dominant, which is now the capital Y. Then the trait for being round is still also dominant, so that is capital R. So a plant that is producing yellow and round peas, that plant will have its genotype, yellow and round. Those are two traits. Yellow is color, round is shape. So color is coded for, in this case, by a homozygous dominant. So Y. Shape, round, is also coded for by a homozygous genotype, capital R. So this plant, which produces yellow round peas, we are crossing or we are allowing it to mate with another plant that produces green and wrinkled peas. We indicated here that the trait for being green is small y. The trait for the allele, the recessive allele for being green is small y. The allele for being wrinkled is a recessive trait, which is small r. So it means for us to have the recessive trait expressed, then it must be homozygous recessive. So that's why we have both small y's and both small r's. Because tukikuwa tuna y kubwa hapa, it will not be green. Instead, because the yellow is dominant. If we have a capital R, the round is dominant. But because it is green and wrinkled, lazima yote ikuwe ni recessive. Homozygous recessive. Okay. So the parent that has yellow peas that are round, that is a homozygous dominant genotype, will produce gametes that have capital Y, capital R. Okay. Then the parent that produces wrinkled green lazima ikuwe na homozygous recessive. So Y ndogo mbili, R ndogo mbili. The gametes it can produce zote tu ni Y ndogo na R ndogo. Okay? Yote ni Y ndogo, R ndogo. So if we now allow these two to breed, so these two gametes, we'll see that in the pedigree. The offspring that they will give us is a capital Y, small y. Capital R, small r. So that's why we are ending up with these offsprings. Okay? So we had homozygous parents, but they've given us heterozygous offsprings. Why? Because they were homozygous, one dominant, the other one recessive. So in this case, if you look at the phenotype ya hii offspring, this one, it will be yellow and round. Why is it yellow and round? Because Y is dominant. R capital is dominant. Y codes for yellow color. R codes for round shape. Okay. So let's now proceed and have a look at the Punnett square in this case. Okay. So I hope you can see it's a dihybrid cross. As I explained, we have a yellow round fruit plant crossing with a green ringgold fruit. The F1 generation that we've seen, all of it is a yellow round phenotype. That's the F1. Why are we getting this? Because all the capital Y's, this is a homozygous dominant crossing with a homozygous recessive. So the dominant allele will mask the recessive allele. The yellow color is dominant over the green color. The round shape is dominant over the ringgold shape. That's why we have all the F1s as being round and yellow. Yet we had a green but ringgold parent. Okay? So in this case, we are having a heterozygote situation, but now the dominant alleles are, we say they are masking the recessive alleles. So let's now cross the F1s to give us an F2. So we self them, which means we cross this with a similar genotype. Okay. So that's why now we have the YR hapa, then Y ndogo na R kubwa hapa, then Y kubwa na R ndogo hapa, na Y ndogo na R ndogo hapa. Okay. So when you have the two genes, two traits, when we are generating gametes from those, we come up with 4, because the traits are 2 that we are looking at, and each of these traits has a possible set of gametes that can code for it. So because we are selfing, we'll have a male with the same and a female with the same. All of them are from a heterozygous parent. We are selfing the F1. So when we self the F1, the YR that are dominant, both of them from the parent, from one parent male and another parent which is female, they'll give us a homozygous dominant. Then the Y and R which are dominant, when they cross with a Y recessive and an R dominant, they still give us a Y dominant which masks the recessive R, the recessive Y, but the two R's were dominant. So you end up with a yellow round. The Y dominant R recessive crossing with the Y dominant R dominant gives us yellow dominant R dominant and R recessive. R dominant masks the R recessive. The color here also becomes yellow round. The same thing for this. Yellow, the Y that is dominant over the recessive Y. The Y that is dominant masks the recessive yellow. The R that is dominant masks the R that is recessive round. When you now have the greens, it means for you to have a green color is a recessive trait. Inamaanisha hapo yellow ni recessive homozygous, so utakuwa na Y ndogo mbili. So anywhere there is green inamaanisha kuna Y ndogo mbili. Anywhere penye kutakuwa na ringgold itamaanisha kuna R ndogo mbili. So the R recessive, ringgold is a recessive trait. It can only be expressed when you have two recessive alleles. Okay? When you have two recessive alleles. So in the F2 generation, in the F1, we had all of the offspring in the F1 generation being yellow and round. But in the F2 generation, now we end up with a ratio that is very interesting. 9 to 3 to 3 to 1. So 9 that are yellow and round, 3 that are yellow but green, then 3 that are wrinkled but yellow, then 1 that is green and wrinkled. Okay? So when you follow this Punnett square, you will see where there is yellow, where there is green, where there is the wrinkled color. In this case, we've used a Punnett square to see how a dihybrid cross can happen. Dihybrid cross is when you have two traits, two characteristics of an organism. In this case, we are looking at color and shape. Looking at color and shape. Okay? So when you do that, then now you end up with a bigger Punnett square. Okay? So if you know the noise, I'm doing this from the university and we have a bit of student politics. So wanafunzi wanaimba hapo nje kidogo. So let's pause for a minute. Waimbe wapite then tuendelee. But as we do that, just have a look at this Punnett square. We'll continue in a minute. So, in a dihybrid cross, if you are dealing with parents that are homozygous, one is homozygous dominant, the other one is homozygous recessive, for both traits and alleles, then your F1 generation yote itakuwa na a common phenotype, which is the dominant phenotype. But now when you go to the F2 generation, then you have now the phenotype in a ratio of 9 to 3 to 3 to 1. Okay? 9 to 3 to 3 to 1. Study that Punnett square on page 8, the figure 5. Then if you don't understand it, reach out to me and I'll explain it to you properly. Okay? I'll explain it to you properly. But it is properly explained up to page 9. It's properly explained. So, on page 10 now, we have an interesting photo. Okay? Have an interesting photo. Kuna watu, you look at their hairlines, there are people who have a point in their hairline, a sharp point at the center of the forehead. But then there are others who will not have that sharp point of hair. So kuna wengine itapita too straight na kuna wengine they will have a sharp point. Okay. So for those who have a sharp point, we call that the widow's peak. So someone who has that is referred to as the widow's peak. So the widow's peak refers to a point in the hairline at the center of the forehead. Okay. So kuna wale watu nywele yao inakuja hapa hivi inakuwa na mwana. But there are others who don't have that at all. Okay. So such occurrence of that sharp point, which I am now calling the widow's peak, that is a genetic trait. But it is it's controlled by just one gene located on an autosomal chromosome. Okay? So that's why we are referring to this as an autosomal single gene trait in humans. So if we assume, for example, that the dominant and recessive alleles for this widow's peak are represented by capital W and small w. So capital W is dominant, small w is recessive. So then for someone to have a dominant, to be homozygous dominant, that person will have WW. Okay? Then a heterozygous for that it will be capital W, small w. So homozygous dominant is capital W, capital W. Heterozygous is capital W and small w. In terms of phenotype, both of these two people will have the same widow's peak, whatever will. But only people now who are homozygous recessive, the small w. So WW small, those are the ones who will not have that widow's peak. Okay? Those are the ones who will not have that widow's peak. So the occurrence of that is also a courtesy of a genetic trait. It means there are alleles that code for it. But for you to have it, it means you've inherited it either as a dominant or a heterozygote. But anything else, then you don't have it. If you have it as a homozygous recessive, then you will not have that widow's peak. So nywele yako hapa haitakuwa na hii point inakuja wengi inakuwa tu straight. Let's have a look at sex inheritance. So the determination of gender. Okay. So we've said we have 23 pairs of chromosomes. And one of those 23 ndio inakuwa a sex chromosome. So the X, Y. Then the other 22 are autosomes. Okay. So we mentioned that when you have two X chromosomes, that's XX, that is female. Then when an individual has just one X chromosome and another Y chromosome, that becomes a male. That becomes a male. So if there is a baby who has inherited an X chromosome from the father and an X chromosome from the mother, that child will be a male. But if a baby inherits a Y chromosome from the father and an X chromosome remember the mother can only give an X, that's all she has. So it is the father who can give either, but the mother has two X chromosomes to give. So then it means it is the father who determines the sex of a child. Okay? It is the father who determines the sex of a child. Okay? There is only an interesting bit. So you have an illustration on figure 7 to show you there is a father. The small one is the Y chromosome. So you realize it's the father who has a big X and a small Y chromosome, but the mother has two X chromosomes, which are homologous, they are equal. So any of the offsprings, when you anapata the small is the Y. So getting a Y chromosome automatically makes your son, makes your male child. Okay? It makes your male child. We've said when you inherit a Y chromosome from your father, automatically you become male. Then if you inherit an X chromosome from your father, you automatically become a daughter. So it is what you inherit from your father which determines your gender. But there is only just an interesting fact on an aspect of timing. So the Y sperm, the Y chromosome, which will be likely. So the sperms from the father, there are some which will be having the Y chromosome, the other one will be having the X chromosome. So the Y chromosome will swim faster, but it dies quickly in an acidic environment. Then the sperm carrying the X chromosome, remember that is now what will lead to girls. It will swim slower, but it will live longer in an acidic environment. So the woman's body is naturally more acidic. Okay? So if you are trying to have a son, then time intercourse to be as close as possible to ovulation. Okay? So the closer you get intimate with your wife, when she is almost ovulating, you increase chances of getting a son. Okay? Because the faster Y chromosome itaenda ipate mayai kama iko tayari, then there will be fertilization. Okay? So let's look at now some of these X-linked traits in humans. Okay. So an example of a sex-linked trait in humans is color blindness. So there are people who cannot differentiate, for example, between red and green. Okay. So we'll see the inheritance pattern in figure 9, and we'll explain it later. But in this case, a male only has one X chromosome and a Y chromosome. So it means then males are more likely to be colorblind than females, because color blindness is a sex-linked recessive trait. If it is a sex-linked and it is a recessive trait, it means for it to be expressed, it has to be either present as the only one or present with another recessive. So because the male only has one X chromosome, if that X chromosome that you've inherited from your mother, if it carries the color blindness trait, then automatically you have it, because you don't have any other X chromosome yenye unaweza sema it will be carrying the normal trait ya kutokuwa colorblind. Okay. Because as a man, you will be having the Y chromosome from your father and the X chromosome from your mother. So if your mother was a carrier, as a woman, she had two X chromosomes. So possibly, she had one of the X chromosomes having the trait, having the gene that brings about colorblindness, that has that recessive trait for colorblindness. Then she had the other X chromosome having a normal ability to differentiate between red and green. So the red and green, the ability of the other X will mask this recessive trait. But if it happens that you have inherited that X chromosome carrying the recessive trait as a man from your mother, you don't have any other X chromosome, then that recessive trait will be expressed, the color blindness. So you end up now having more males being colorblind compared to females. Why? Because color blindness is linked to the X chromosome. So if the X chromosome that the male child has, yenye alipewa na mama yake, it had that recessive trait, then that is the only X chromosome that the son will have, so that trait will be expressed. But if the daughter is inheriting the similar X chromosome from the mother, but the daughter will be getting another X chromosome from the father. So if the father had the normal one, the ability to differentiate between red and green from the father is normal, then the father's normal red-green ability that is linked on the father's X chromosome itafunika the recessive trait imetoka from the mother's X chromosome. So because the female child has two X chromosomes, she will end up not to be colorblind. But because the son can only have the one from the mother, if the one he is inheriting from the mother has the recessive colorblind trait, then the son does not have any other X chromosome, ni too, so that trait will be expressed. So color blindness is an example of a sex-linked trait that is found in a given gender more than the other. Okay? That is found in a given gender more than the other. Let's have a look at a Punnett square in table 1 below, where there is a son of a woman. The woman is a carrier of color blindness. And if this woman bears a son, has a son with a male, okay, so let's see how that inheritance pattern looks like. In table 1 is a Punnett square for color blindness. So when you have the recessive one is the small b, but the capital B is the normal one. So if you have the capital B, then it is not, you're not affected, you're not colorblind. But when you have the small b, if you are a son, you are colorblind. If you are a female, you are likely to be a carrier, depending on the other X chromosome that you have. So in the case where you have a woman who has a normal B on the X chromosome, then a recessive B on the other X chromosome, which means now the woman is a carrier. This woman is getting married or is mating with a man who is not colorblind. The man is not colorblind, but the woman is a carrier. So let's look at what happens with the children that they are likely to give birth. So it is possible, on the basis of this Punnett square, that one child will inherit the recessive trait from the mother and the normal one from the father. So the normal one from the father will mask the recessive one from the mother. So that is an XX, that is a female who is a carrier, will not be colorblind. If another female child will inherit both normal ones, normal X chromosomes, one from the father, one from the mother, it ends up as a female who is not affected. So in terms of phenotype, this is not colorblind, this is not colorblind. Let's look at now what happens. The presence of Y gives us males. But if the male is inheriting an X chromosome that has the normal trait, not the recessive trait for color blindness, that male will not be affected. So that's why we are saying unaffected male. But if the male child, a son to this couple, inherits the X chromosome from the mother, which carries the recessive trait, then that son will be colorblind. So why is it that the son is inheriting this recessive trait? Our daughter is also inheriting the same recessive trait, but it is only the son who is becoming colorblind. It is because the son does not have any other X chromosome, but the daughter is inheriting a normal X chromosome from the father. But the son will have inherited the Y chromosome. So Y chromosome does not have any gene that will help to mask this recessive one. So the recessive trait in the child who is a son here will be expressed. But the recessive trait carried by the female will not be expressed. Why? Because the female child inherited a normal X chromosome from the father, but they now inherited a recessive an X chromosome linked to a recessive allele for color blindness from the mother. So the normal one from the father will mask the recessive one from the mother. But now the son does not have any other X chromosome apart from the one which the mother gave him. Okay? Now you end up with this recessive trait being present in a particular gender more, just because of what? It being linked to a particular chromosome. Okay? So that is still being shown even in figure 8. So table 1 is a Punnett square, but figure 8 is a pedigree. Figure 8 is a pedigree. Okay. So an example of another recessive X-linked trait is hemophilia. Hemophilia is where blood does not clot normally. Okay. So that one can also be transmitted more to the male children, just like color blindness. So any recessive X-linked trait, any color blindness, hemophilia, is likely to affect more sons than it would affect daughters. In figure 9, you have a test for color blindness. So if you are able to read this number, if you are able to read that number without difficulty, then you don't have this red-green color blindness. But if you have a difficulty with that, then you are likely to be suffering from this red-green color blindness. And trust me, more males will have that inability to read this value, this number, compared to most female students in class. Okay? So this is just a test of the red-green color blindness. So the genetics stops here, but the next just gives you why, when you are colorblind, some of the things that might be difficult for you. So one of it is kuvaa nguo. You might end up clashing. Kuvaa nguo hii na hii, you're not able to match your clothes, okay? Because there are people who are so particular with the colors. Akivaa hii nguo anataka aweke na hii, red iende na hii. But if you are not able to distinguish between those colors, then you are likely to do what people call color clashing. Okay? Then many other things, people who, traffic lights, kuna red, kuna green. So if you are not able to differentiate between those two, then you don't know when to go and when to stop. Okay? And many, many other examples. But bottom line is that inheritance patterns will depend whether the gene is located on the autosome or on the sex chromosome. Okay. So that is what is important. Then now, when you are using a pedigree, when you are using a Punnett square, they help you to study those patterns of inheritance. Okay. I hope you will enjoy the video when you read through the notes as you listen to the explanation. And should you have a challenge, feel free to reach out, then we can always explore. So thank you very much, and I hope to see you